So, today's agenda is that we will look at an example which is reasonably detailed, but using the example using Euler-Lagrange, and the basic issue is if you make it two. If you take a three-dimensional problem, then you cannot follow the analysis, you can only do numbers. Okay. On the other hand, if you are dealing with a two-dimensional problem, then your matrices are small and you lose out on some things here and there, but still you can get a reasonable feel of the problem and it is tractable. Okay. So, we will look at this, and I have uploaded this problem and one more problem for you to look at, and obviously in the major you will get a third problem, okay, which is not this problem, not the other problem given in the assignment. The other one is simpler actually, it just has two translating arms, so life is very easy there. So, now we look at the two link planar arm, and even though this looks it is in the plane, it is in a vertical plane, okay, because I want to look at the gravity loading also. If it is completely in the horizontal plane, then the gravity loading does not come into the picture. Okay. Now, by choice I shall not upload this PPT, okay, so that you do a little bit of work on your own. Okay, the problem is uploaded in Sakai so that you can download, but this PPT I will not upload, you need to do a little bit of work. But this is such a standard problem that if you look around on the net, you will find it solved somewhere or the other. So, it is not such a big deal, but at least do that much amount of work. But you can also solve it equally easily in MATLAB, it is quite trivial. Okay, so, we look at this two link planar arm, and so we have basic parameters. This L1 is the distance from this joint to here, L2 is the distance from this joint to here. Then we have these parameters A1, A2, M11, ML1, okay, which is basically the motor at link 1, and you have all these parameters and the mass associated with those links. So, now given these parameters, so the first thing we would need to do is to calculate the kinetic energies. We started by looking at these Jacobians, where each term is either, we do not have prismatic joints, okay. We have only revolute joints, so it will be of the term P z minus, so it will be z j minus 1 into cross product of a vector from the origin to there, right. So, if you look at this term, this is Pj, and for the O term there is only Zj minus 1. Okay, so, these are the two terms which are there. So, now if you look at this term which is here, so how will you get these terms? So, all the z vectors are along the z axis, so they are orthogonal to this plane which is here. So, when you take the product with respect to vectors which are going from here to here, what will you get? You will get two components, right, which are orthogonal to this line essentially. So, you will get a vector which is somewhere in this direction. So, it will have a x component and a y component, and you can check out that the x component is L1 S1 and the other component is L1 C1. Okay. So, these are the two components you land up with. So, similarly, when you are looking at the second link, okay, so there will be two terms. So, one corresponding to this length times sin theta 1 2, right, which will essentially be, I mean there is So, you are essentially looking for a vector from here to here and the cross product with the z axes which are out of the plane. So, you will get one component which is here to here, so perpendicular to this along this direction. You will get another component which is here to here, so orthogonal to this, so in this direction somewhere. So, one of them is this. So, A1 is this length from here to here, so A1 into sin 1, A1 into cos 1 here, and then this length L2 times sin 1 2 and cosine 1 2. So, this is very similar to the old Jacobians that we have studied. So, you can then create this Jacobian matrix for JPL1. Now, the angular velocity component of the Jacobian, this is very easy, this is 0 0 and this along the z axis, and for this one you have two ones because the angular velocity of this link is angular velocity of this link plus the angular velocity of this. You do not need to do this in such a open form, intuitive form. You can essentially go through and simply do it one axis at a time by cascading the things together. So, that is how you are supposed to do it. If you have to look and feel your way through, then there is no point using the Euler-Lagrange approach. Okay. It is a relatively foolproof, safe method. You just might compute a little bit more, but which is okay, because it is not every day that you compute the dynamics of a manipulator. You will do it, well, if you are as lucky as me, you will do it once a year. Okay. For those unlucky souls who will get into investment banking or something, you will never do it. Okay. So, it is not very often, and the Euler-Lagrange method gives you a very systematic way of doing it, relatively foolproof, okay, unless you make a programming error. So, you cascade and you create these two matrices. Okay. So, next thing we have online is, if you look at this, is that we were looking at these, the moment of inertia terms, okay, and how these are being modified by the rotation matrices, because I am calculating the moment of inertia in local terms. Okay. Now, in this case, the rotation matrix does not play a significant role, okay, because we are primarily interested in rotations about the z axis, and the links are rotating again only about the z axis. So, the moment of inertia component about the z axis stays invariant under rotation. The only thing is that the parallel axis theorem has to be applied. Okay. So, this is the catch. The parallel axis theorem has to be applied, and that is automatically trapped in by the formulation. You do not have to work very hard for that, because the way the Jacobian matrices are calculated, that automatically accounts for the parallel axis theorem and the fact that different moment of inertia are reflected differently. So, this inertia matrix tensor, we said that it reflects many of these properties, okay, including the parallel axis theorem and everything is captured in this. So, we do not have to worry about it in this formulation. So, effectively we can use the scalar moment of inertia without any problems, and finally, if you use as the KRI as the transmission ratio, so KR1 and KR2, you can write the Jacobians for the motors, which are little different from the Jacobians for the links, because there is a transmission ratio connecting the joint rates to the motor rates. If the motor goes at an omega I, the joint does not go at omega I, it goes at omega I times the transmission ratio. So, this is the modifying factor which was discussed when I did the formulation. So, you simply accumulate them and you get these two matrices, again the Jacobians for the motors. So, you can then build up the full inertia matrix, and so you can calculate term by term exactly the method which is given there. You just expand it out and you will get expressions like this, slightly longish expressions. Okay. On second thoughts, I will just upload this also, so that you can compare them. So, you will get composite terms like this, which involve moment of inertia of link 1, the transmission ratios and things like this. And then there is this cos theta 2 term which is here, there is no other term involving theta 1 in the inertia matrix. Similarly, in B2 there is a cos theta 2 term, and in B22 there is no cos theta 2 term. Okay. So, there are these 3 terms which are dependent on theta 2, which is not unexpected, because if you go back on this figure, it is only this reconfiguration of theta 2 which will change the moment of inertia of this combination about this joint, right. As theta 1 changes, the moment of inertia seen about this joint does not change, right. So, in this example, only change in theta 2 will change the moment of inertia effectively seen at joint 1. Okay. And change of theta 2 does not change the moment of inertia seen at joint 2. So, that is why when we get the final expressions, it turns out that B22 is not dependent on, it is actually invariant, and the other 2 terms B11 and B12 and B21, they are dependent on theta 2. Okay. Then here there is another interesting phenomenon which you should know, this gets into practical design issues. You have this term here which is Kr2 Im2, which is moment of inertia of the motor shaft of motor 2 multiplied by the transmission ratio. If you look at these terms here, you have Kr2 square Im2. It is not unusual to have a Kr of 50 or 100 in a DC motor, because you want to increase the torque, and usually speed is not an issue, because most DC motors comfortably run at 5000 rpm idle. So, under some load they will easily run at 1000 rpm, and you know that you do not want the robot to move around at 1000 rpm is how many hertz, 30 hertz, no, divided by 60 hertz, what am I doing, it's 100 by 6, 18. Okay. So, you do not want it to go around 18 times in a second, right, you do not want it. In fact, you do not even want it to go around once in a second, that is too fast. So, it is not unusual to see a reduction ratio of 50 or 100 from the motor, not necessarily by the belt that we have shown schematically in our analysis, but it could be through gearing. So, it can be made very compact, especially if you are using epicyclic gearing or something. So, when you have such a large, so this term Kr2 square Im2 is significantly larger than Kr2 Im2, and since both of them, you look at B12 and B22, they will finally get multiplied by theta 2 dot or theta 2 double dot. So, this term will have a significantly larger contribution than this term. Okay. So, what is often done is, when you are formulating dynamics, you will simply drop this term, you say this is 50 times low, I will not be able to feel the effect of it. So, then in this process you start simplifying your dynamics. Okay. So, when I remember I mentioned that you eventually drop terms, or you design it such that it becomes more amenable to the solution process. So, these are kind of decisions which you make. Okay. So, if you do this, then you get these motor inertias appearing only in the diagonal elements of the inertia matrix, which makes life a little bit easier finally when you are doing your computation. So, then you can you can just reflect it. So, since this is this Kr2 square Im2, so this will get clubbed. So, if you are dropping this term, so then you can club these 2 terms together and just run it together. So, you do not have to do that separately. So, then the nice Christoffel symbols, right, which is the real takeaway from this course. So, you can easily calculate them. So, C111 is half, partial of B11 with respect to Q1, we just go back, B11 is this, there is no dependence on Q1, it is only dependent on theta 2, not on theta 1. Okay. So, this term is equal to 0. You can similarly calculate what the other terms are. Okay. So, you get this all this C11, C12 essentially becomes everything is minus MA L2 L1 this term. So, you are just calling this H. So, this is only one term which is there. C212 is 0, C222 is 0. Okay. So, based on this you can form the C matrix, okay, and it is quite simple. So, how do you form the C matrix? So, we are just summing up like this, Cij ij is equal to Cij k Qk and summing up over one of the variable sets. So, what I have done is I have calculated the Cij's, I just need to sum it up with Q1 Q2 dot. So, you will get a term like this. Here I have two of them and both of them are present. So, H times theta 1 dot plus theta 2 dot. Okay. So, you just follow through like this and you can form the C matrix, and then we can check for skew symmetry. We have the B matrix. So, we can find its derivative quite easily, and then once you do this, so I get back this value. So, I know that I have done things okay, or at least one part of it is okay. It is validating that this N matrix calculated in this form B dot Q minus 2 C Q Q dot is equal to is a symmetric matrix, a skew symmetric matrix. So, this is minus 2H and this is 2 plus. So, plus 2H theta 1 dot plus H theta 2 dot, this is minus H theta 1 dot minus H theta 2 dot. So, the skew symmetry is verified. So, that means I can rest easy. I have done so far, I have done things okay. I would seemingly have done things okay. So, then you need the gravity term. So, you need the potential energy term only if the planar manipulator is in a plane which is not truly horizontal. So, if it is an inclined plane, you will need that, except that G will have a component. So, we make life easy for ourselves, we just assume it is in a vertical plane and G is along the negative y direction. So, use G0 minus 0 minus G0. If you are doing 3D, usually it will be 0 0 minus G in the negative z direction. So, there are two terms here, one for G1 and one for G2. So, you have this U term here which you can calculate like this. So, we are doing the same thing using the same Jacobians that we have used for the kinematics, and then so then we will end up with, finally we will calculate this thing is equal to GIQ. So, these are the two terms G1 and G2 that you get. So, if you neglect such real life effects like slip and friction, you will end up with two equations. So, this all of this becomes equal to tau 1 and all of this becomes equal to tau 2. Okay. So, that is quite well, it is a little bit more complicated equation than what you have written for your mechanics courses, but it is not very complicated, it just has so many terms. If you do any heat transfer problem, or you have many more terms. If you are looking at a power plant, you will get many more terms. There are so many recirculations and expansions and contractions and compressions, heat exchanges. So, those are more complicated. So, this is a relatively simpler expression, and obviously because it is a small 2-link planar manipulator, and then you can track it and you can associate many terms, many terms will appear to be familiar. And obviously but you can run some basic checks. See, all these terms are actually square terms, see L1 squared, then L2 squared, A1 L2 is a length. So, these are small things which you can check as you go along to see whether things are okay. Okay. And So, the next thing on the line is to look at what happens when you start plugging numbers in, which is the real final solution. So, you can take A1, A2 1 meter, L1, L2 0.5 meters, some value of mass, some value of moment of inertia of the links. Usually it is suggested that you take reasonable values. Okay, if you take unreasonable numbers, then things go topsy-turvy and scaling becomes very bad. You can't observe any effects which are of interest. So, you can pretty much model it in Pro-E or SolidWorks, whatever is your favorite tool, and then back it out from there. So, we then assume that you have the tip initially at 0.20 and you are going to make a rotation of pi by 2 about each joint in 0.5 seconds. Okay, so, that is the task, and you are going to do it by going through a trapezoidal profile. Okay. And so, if you do that, then you will get some kind of a parabolic biparabolic shape here, and the acceleration will be constant in this phase and then negative and of the same value in this phase and 0 here on. So, this is quite standard. So, we so far done only kinematics. Okay. So, now I want to look at some more numbers. So, what is plotted here? You have joint 1 torque and joint 2 torque. Okay. Now, if you look at the torque as a composite, then you can see it is somewhat like the acceleration profiles. Just flip up. Okay, this is the acceleration profile down here. Excuse me. So, this is similar, but you can see that this is the acceleration profiles have been modified a bit. However, if you look at the inertial contribution, since I am calculating it using matrices instead of just measuring the joint torque, from the analysis or from my MATLAB I can exactly find out what is the inertial torque over a period of time. Okay. If I look at only the inertial torque due to link 2, due to the acceleration of link 2 on link 2, then you get a curve which is exactly the same as the acceleration plot. Okay. However, the torque due to acceleration of link 1 on link 1 is slightly modified. Okay. Now, can you tell me why is this? A little bit of thought. Sorry. So, when I showed you the inertia matrix, I kind of pointed out that this is invariant, right, and this one is dependent on theta 2. So, the moment of inertia is not constant. So, even if the acceleration is constant, right. So, theta 1 and theta 2 have the same acceleration profiles, but because the moment of inertia seen by the link 1 is not a constant, it is variable, that means you have a modification to the curve. Okay. So, you have a modification to the curve. Okay. And finally, if you look at the other two terms, the forces due to the torques due to the acceleration of link 2 on link 1, torque on link 1 due to acceleration of link 2 and due to torque on link 2 because of that. Now, those two terms are symmetric. So, these two torques also turn out to be symmetric. Okay. So, this is the basic structure. So, then there is the Coriolis, quote unquote Coriolis term, okay, which you can extricate, you get a term. So, the arm tip moves with respect to the frame attached to link 1, but is fixed with respect to the link 2. So, you do not have, you have Coriolis effect, it is visible only at joint 1, it is not visible in joint 2. So, centrifugal effect is both there and they essentially reflect the, so this one being very similar to this one, so that essentially reflects the symmetry of the inertia matrix also. So, these are observable figures, effects of from the analysis, and it is pretty much in par with what you expect for this 2-link manipulator, and so you can play around with the numbers, get an estimate of what happens when you have different forces and torques coming on the structure. Okay. So, we use the next 10 minutes to talk about the Newton-Euler formulation. Okay, we will take it up in earnest starting tomorrow. Okay, so what is the Newton-Euler formulation? So, we have the same joint or the same link motor combination that I looked at earlier, and the basic difference is you do force and moment balance on individual links of the manipulator. In the Euler-Lagrange formulation, you just wrote the total potential energy and the kinetic energy over the whole system, and then you took some partials with respect to some generalized coordinates. So, here you are going to write a force and a moment balance equation on individual links of the manipulator, and in doing that you recognize that, so if this is a system, so at this end this is connected to another link, to another joint, and here is connected to another link to another joint. So, there is a force acting which this link imparts at this joint, which I am calling Fi. There is a force which this other link imparts at this joint, which I am calling Fi plus 1 with a minus sign. Okay, minus sign because I will have to evolve a sense, because the force applied, if I am referring to Fi plus 1, I have to decide whether it is the force applied by the ith link on the I plus 1th link, or it is the force applied by the I plus 1th link on the ith link. So, by convention what is being followed here is that Fi is the force applied by the on the ith link by the I minus 1th link. That is the convention that is being followed here. Now, there are several conventions, each guy follows his own, whatever is convenient to that person, depending on who is taught him or which book he is following. He should pretty much, it is the same thing. This is convenient because if you do not want to use this, you have to get into a 2 index formulation, okay, which writes, you would write either I minus 1 Fi, okay, which is the force applied on the ith link by the I minus 1th link, and then for the other one you would write If I minus 1, force applied by the ith link on the I minus 1th link, and then you would know that they are negative of each other. So, this one is convenient, especially if you are customizing it for a serial manipulator. So, this method creates a problem when you are using it for parallel systems, because then once you complete the loop you are in trouble, but it works okay for serial manipulator, which is the task which you are looking at right now. Similarly, at these points you have these moments. Now, the moment vector and the force vector need not be along the same line, even though this is the joint axis, and they need not be along the same axis. Okay. So, it is very clear that they need not be on the same axis, and then you have the center of mass, you have all these vectors which we talked about, Ri, then there is center of mass Ci, then there is omega I, and then there is the motor I plus, which is essentially related to omega of this through the transmission ratio R, all of transmission ratio K, all of them are pretty much the same thing that we dealt with in the Euler-Lagrange formulation. And The crucial thing is we have these 4 additional structures which are there. Now, in this formulation, so to work on this I need velocities and accelerations. Now, to get velocities and accelerations I need to start from the base link and I need to do forward kinematics given q1, q2, q3, q4 and then q1 dot, q2 dot and their second derivatives. I need to keep marching from the base link where I know that everything is 0. So, I have to keep marching forward to find out what all the accelerations are. So, there is a forward recursion. Now, on the last link, the advantage I have is that in the last link I only know, I know that there is a set of forces which is applied here at. So, I know in the last link that there is only one set of forces acting here and anything else which is external to it, I have numbers for it. If I take an intermediate link, then I have these 4 unknowns. I do not know this, I do not know this, I do not know this and I do not know this. If I take the last link, I have only 2 unknowns. I do not know the forces and the moments, but I know everything else. So, these force and this moment they give you 6 unknowns, right, and you have exactly 6 equations because you have 3 force balance equation and 3 moment balance equations. So, you can solve for this. So, sitting on the last link you know all the forces, you can solve for this force and moment, then you know all the accelerations, so you know all the inertia terms and everything. So, you can solve this, you solve this force and moment here and then you keep marching down until you have all the forces and moments. So, that is the basic approach which we will follow. So, you have the Newton's equation which is Fi minus 1 plus Mig0 is equal to mass times accelerations or the center of mass. So, it is quite simple and the Euler equation is essentially the same thing, moment times the forces cross with the moment arms minus this moment minus force cross with the moment arm, and this has to be equal to this term, the rate of change of essentially angular momentum terms of this of the motor shaft. So, and modified by the transmission ratio and the fact that this q dot is the q of the next link. Okay. So, in the moment equation there is no contribution due to gravity, it is there in the force equation because that is by definition the concept of the center of gravity, okay, and we write the equations about the center of gravity so that this goes to 0. Okay. So, that is the contribution, but written in this form using II bar is not convenient as we have seen for the Euler-Lagrange equation. Okay. Why is it not convenient? Because it will keep on changing and we cannot establish it. So, what is done is you use the moment of inertia of the link in the current frame in which it is invariant and you multiply it with the rotation matrices to convert it into the global frame. Okay. So, when we start in the next class, we will kind of take off from here and just formulate it, and hopefully we will end up doing the same problem that we did today using the Euler-Lagrange approach and then see what is the convenience and the inconvenience of it.